So, maybe I should start off trying to kind of set a bit of the stage for kind of where I think the science we're doing is at and where it might be going. I mean, it's an exciting time because I think we are succeeding in kind of unlocking things in a whole variety of kind of foundational questions about various areas of science. I did not expect this was going to happen. What really launched the current round of excitement was our physics project that got launched in early 2020, and that's kind of opened up a lot of new directions, not only in fundamental physics, but also in foundations of mathematics, foundations of biology, foundations of machine learning, and I think also sort of upcoming excitements, foundations of theoretical computer science, foundations of economics, and so on. How could this possibly be happening? Well, I think the main point is that there's kind of a paradigm that we've come upon that is applicable to these different areas. I mean, if one looks at the progress of science, it tends to kind of make jumps every time some new methodology, some new paradigm gets invented. And I think we're in the middle of such a jump, which is pretty exciting. Not what I had expected at this point in my life, but I'm happy that it's happening, and we all get to be part of the story. So, kind of the original backstory of all of this had to do with the work that I started doing at the beginning of the 1980s. That was the following. Had to do with the following question. I mean, when I was a kid, I worked in physics and particle physics and cosmology and things like that, and learned all these fancy techniques from quantum field theory and general relativity and all of these kinds of things. And it was a cool thing because in the late 1970s, that was a time when sort of a bunch of new methodology was being found to be applicable, particularly from quantum field theory and so on, and sort of the beginnings of the bridge to cosmology in particle physics. And so the then teenage me was able to work on a bunch of things that had just been sort of opened up at that time. And that means that stuff I did when I was a kid is still getting used today, which is really nice. Even though, because I happened to be involved in that field at a time when there was kind of rapid growth possible because of new methodologies opening up. So in any case, back beginning of the 1980s, I was interested in sort of foundational questions, and I particularly was interested in what seemed like a fundamental question about the world, which is how come there's so much complexity in it? How come there are so many systems, whether it's a snowflake or a turbulent fluid, or at that time I was interested in the formation of galaxies and things like this, or for that matter, biological organisms. How come there's so much complexity in the world? Where does it come from? Can we explain it? So my sort of plan A was, let's just use all these fancy techniques we know from mathematical physics and so on, and let's figure out the examples of snowflakes, fluid turbulence, whatever else. Let's just figure out how they work using all those fancy techniques. This was a bust. It absolutely didn't work. There were, you could write down differential equations, you could make them do various things, but they didn't do the kinds of things that one actually observed in nature, and particularly didn't do the complicated things one observed in nature. So I kind of went to, plan B, which was, okay, let's try and make some new fundamental models for what's going on, and let's try and see whether we can understand from those why we're seeing all this complexity in nature and so on. And so that led me at first to cellular automata. I mean, I kind of was trying to make a model that was sort of a minimal model. Actually, I had sort of two objectives in mind. One was thinking about brains and neural nets, and one was thinking about galaxies and self-gravitating gases. Well, somewhere in the middle of those, somewhat inspired by things like the Ising model from statistical physics and so on, I came up with these, what I later learned other people had named cellular automata, these kind of very simple models with which I'm sure you guys know about, and if not, you'll certainly hear about in the coming days. And let me not go into too much of the science detail of these things, but we're just dealing with some grid of cells and a simple rule that updates those cells. And the sort of big surprise, the big surprise is, if we look at, let me make this a bit bigger. We have that little rule that says how to update the colors of cells. And if we run that rule, let's say for 40 steps or something, we get a pattern like this. Very simple rule, complicated pattern. Run it instead for 400 steps, and you get an even more complicated pattern. And this is kind of, I first made this picture in 1981. I first understood the significance of this picture in 1984, which kind of tells one something, and we'll talk about this a little bit later, about kind of doing computer experiments and sort of the challenges of doing science in general. But kind of the big surprise here was very simple rule, single black cell at the beginning, very complicated pattern of behavior. It was something that I didn't understand for a couple of years, partly because it kind of violated my intuition about how things should work. It's like it shouldn't be the case that you can start off with such a simple rule and get such complicated behavior. And I spent a while trying to say, there's got to be a way to analyze what happens in this pattern and see that it really comes from something simple. And that didn't work. So what I suppose was the main achievement of those times was realizing that the fact that that didn't work was itself a very important thing. That you could get very simple rules, very complicated behavior, and that was a general phenomenon in the computational universe of simple programs like the one I'm talking about here. And I suppose the big picture for me at that time was kind of the traditional exact science approach had been you write down an equation for that. You solve the equation. What I was thinking about here was something where instead of saying we're going to use the particular mathematical structures that you have in equations, it's like we're going to write down some rule that we can specify in a computational way. We can specify sort of any rule in a computational way, but these are something like the cellular automaton rule is a particularly convenient kind of very simple rule to specify in that way. We write down a rule and then we see what its consequences are. Today, I would call that activity of just writing down rules and seeing what their consequences are rulology, the study of simple rules and what they do. I think rulology is a very fundamental area of science that I guess I've been working on for 45 years or so, although we didn't name it until about 5 years ago. But the kind of the idea is you are specifying some simple rule, then you are working out its consequences, and usually you're using a computer to do that because in practice you're not going to by hand work these things out. And then the other question is, well, are there some fancy methods that will allow you to figure out what's going to happen in, let's say, this Rule 30 pattern without actually following each step and seeing what happens? So one of the kind of big points, conclusions, phenomena that I discovered from doing these sort of experiments in the computational universe is a phenomenon I call computational irreducibility. And I first sort of came up with that term 40-something years ago now. And that's been a really important phenomenon in a lot of stuff that I've done. And I think the big burst of kind of discoveries in recent times have had to do with the interplay of computational irreducibility with the characteristics of observers like us. We'll come to that in a bit. In any case, what is computational irreducibility? Well, there's a question. How do you work out what happens after 1 million steps in the evolution of Rule 30? Well, you can clearly just run the rule just for 1 million steps and just see what you get. That's sort of following the same computation that this system is using itself. But if you are going to say, well, I'm going to be much cleverer than the system, I'm going to figure out kind of a way to jump ahead, a way to use some fancy mathematical technique or something to jump ahead and say, this is what's going to happen in 1 million steps, just by working it out, not by following each step and seeing what happens. So if one's going to do that, that's an example of kind of computational reducibility. It's something one's gotten very used to being able to do in kind of traditional mathematical exact science. You're trying to work out the orbit of some idealized two-body, system, you don't have to follow the million orbits. You just use a formula and plug the number in and get the result. Okay, so the big claim is that in the computational universe, with things like Rule 30, computational reducibility is not a general thing to be able to do. So why is that? Well, the way to understand it is through this thing I call the principle of computational equivalence, which is another kind of big idea. And it's the following thing. So you can think of the process of working out what happens in Rule 30 or whatever else as a computation. And the question is sort of how sophisticated a computation is that? You can think of all kinds of things that happen in the universe, in abstract systems, as computations. You can think about what our brains do as computations. We have certain input, we generate certain output. You can think of what happens in mathematics in that way as well. And the question is, what is the comparison between sort of the sophistication of all these different computations? Well, the big discovery of the 1920s and 1930s was that there's this idea of universal computation, that there exist things that you can create structures, let's say Turing machines, that have the property that one particular Turing machine, by being fed different initial conditions, can emulate any other Turing machine and potentially any other system that does computational kinds of things. So that was sort of the beginning of the path that leads to the principle of computational equivalence. The principle of computational equivalence makes the claim that essentially any system whose behavior isn't fairly obviously simple will turn out to be equivalent to any other system in its computational sophistication. So in other words, that something like Rule 30, there's the computation that's going on, even with a simple initial condition, you didn't program it specially, even with this very simple rule, the computation that's going on is somehow equivalent in its sophistication to any other computation one can get done, at least in our universe, and including the computations we can do in our brains, the computations we can do with math, with statistics, with cryptanalysis, whatever else. Okay, so what does it mean if it's true that all these computations are equivalent? Well, if we're going to try and predict what does Rule 30 do in a million steps, and we're going to try and outrun Rule 30, we in a sense have to have a more sophisticated computation to jump ahead than just following those steps with Rule 30. But the principle of computational equivalence says you can't do that. It says all these different things that you might use as your kind of platform to do that jumping ahead are just equivalent in their computational sophistication to something like Rule 30. So the principle of computational equivalence says you can't make a thing that will kind of jump ahead of Rule 30 and figure out what's going to happen. You're stuck with just following what Rule 30 actually does and seeing how it comes out. And that's kind of this idea of computational irreducibility. And so computational irreducibility has endless consequences, which I'm sure we haven't figured out all of yet. It talks about sort of at a philosophical level, it talks about kind of how determinism, how a deterministic system can lead to something that in a sense has what the appearance of kind of free will, in the sense that you can't tell what it's going to do. It's only by just following what it does that you can see what it's going to do. It tells one that when you do simulations of things, those simulations aren't just a convenience, they're fundamentally necessary to work out what the system does. It tells you things about, I don't know, AI, controlling AIs. It tells you, computational irreducibility kind of tells you there will always be surprises. Any system you set up that isn't simple in its behavior, you will never be able to kind of give constraints that guarantee to tell you everything that happens. There'll always be unexpected things which can happen. So you kind of have a choice with AI. You can either say, let's make all our AIs be computationally reducible, in which case they can't make use of all of those computational capabilities they might otherwise have, or let's allow them to be computationally irreducible, in which case they'll occasionally do things we don't expect. So there are many consequences of this idea of computational irreducibility, and it's sort of a central kind of conceptual feature of the kind of landscape of the computational universe. Okay, well, so I discovered this basic phenomenon in the 1984 or so, and then starting at the beginning of the 90s, I started, I had built, so one very important thing is that I kind of, sort of a critical piece of these discoveries is using tools, and particularly using computers as tools. And kind of, I mean, as the piece of personal history, I had gotten into using computers to do theoretical physics back in the 70s. And I was very surprised that other people weren't using computers to do like complicated algebraic calculations and so on. And I was able to sort of do magic things because I was actually using those tools. And then in 1979, I started kind of building my own tools to do these things, built a system called SMP, which is kind of a forerunner of Mathematica and Wolfram language. But in SMP, it kind of forced me into understanding a bunch of things about the foundations of computation, because that was what was necessary to kind of design the structure of SMP. And it was kind of the knowing about those kinds of computational foundations that kind of launched me on thinking about kind of simple programs as models for systems in nature. Kind of an interesting sort of feature of the arc of the history of science, that back when I started doing that in the early 80s, people were like, that's not how nature works. Nature is governed by equations. We all know, physics has been very successful with having sort of differential equations that describe things. That computers do what computers do, but nature does what mathematics talks about, and equations and so on. People were like, no, it can't be true that that you can make models of the natural world in an effective way with programs. Well, you go 30, 40 years later, and most new models that get made these days are made in terms of rules and programs and so on, not in terms of mathematical equations. So kind of rather silently, that idea of kind of basing models of nature on programs, that idea won. Now, that understanding, just like if you're basing things on traditional mathematics and calculus and so on, there's lots of mathematical structure that's worth knowing in pure mathematics to be able to make use of the fact that you're using those things to model the natural world. Well, so similarly, there's kind of an abstract field that you have to build that talks about kind of how rules work and the kinds of things that happen abstractly when you're thinking about things in terms of simple rules. And that's kind of this field of rulology, the study of simple rules and what they do, and kind of things like the principle of computational equivalence are kind of guiding principles in the study of rulology. But rulology also has a methodology. I mean, it's all about doing experiments on programs and seeing what happens. And those experiments, like other kinds of experiments, there's an art to doing those experiments well. If you do a physical experiment, there's a question: can you really make an isolated system and really kind of, know that the effects that you're seeing are actually a consequence of sort of the things that you put into the system? Can you make a very clean experiment? That's, difficult in physics. It's even more challenging in life sciences. So the same thing is true with computational experiments. Can you make an experiment that's simple enough that when you see a result, you actually know what it means? And so that's one thing. It's also, I've ended up building tools like Wolfram language. Wolfram language is kind of, by huge measure, kind of the thing to use if one is going to do rulology. It's a thing to use for many other purposes as well. But in rulology, it's kind of, I built it partly because I wanted to use it for that, and it's really good for that. And I think that the thing that happens is you kind of, I've been studying lots of kinds of simple programs. In fact, I'll show you one that this is the last few weeks of work. A thing I've been working on about theoretical computer science, and it's about Turing machines. That's a little Turing machine, and that's what it does. And one of the things about rulology is you define experiments, you do them, you define very clean experiments, you try and do these experiments, then you see how the chips fall, and you see what results you get, and you try and understand what's going on. And the thing that amazes me is that after 45 years of doing this, when I do the experiments well enough, I'm always surprised. I'll have some hypothesis about what's going to happen. That's what leads me to do the experiment. If you have absolutely no hypothesis, you're not going to even try and do the experiment. But then I actually do it, and surprising things happen. It's and you have to be open to those surprising things. As I mentioned, when I discovered Rule 30, it took me a couple of years before after I'd actually seen the phenomenon, to understand what on earth was going on and to really appreciate the phenomenon. So, in this case, I was looking at, this is just a post that will come out hopefully soon, and we should see whether there's something that is a surprise. Well, okay. This is an example of a small surprise. This is a Turing machine where it goes along, it starts from an input, gives an output, it halts, and then suddenly, and this happens in much larger kinds of values for other cases, suddenly it doesn't halt. You think, oh, I know, I can kind of use scientific induction. I can kind of say it halted in a bunch of cases. It's going to halt in other cases. But no, that's not the story of computational irreducibility. There's always surprises. And that's a small example of that. And computational irreducibility is kind of the thing that you have to come to terms with in doing rulology. The thing that's really nice about rulology, it's a very wide open field where there's just a huge amount to do. And, I've done some of it. There's probably 500 or so papers of people sort of following up on things I've done and doing other kinds of rulology on different kinds of systems. Maybe 1,000 papers, I don't know. But that are fairly clean, pure rulology, so to speak. The thing that is so nice about rulology is if you do a really clean piece of rulology, some very simple system, like those Turing machines I was just looking at, I had looked at those in the early 1990s as well. And the things I'd done in the early 1990s were kind of still useful and valid today, because what I was looking at was a very simple system, and that's kind of a core thing that's going to show up over and over again. I mean, with cellular automata, there are 256 of the simplest kind, and I literally used to have little file folders of the different applications that were steadily found for different ones of those particular rules, because they're the simplest rules, and they're the good raw material for finding models of things. So in any case, the thing that sort of the great thing about rulology is you build these, you put in these bricks of, you discover this particular thing. For example, this piece I was just writing about P versus NP, the middle of it I found kind of boring. I'm kind of doing natural history. I'm describing, this Turing machine does this, and that one does that, and this is what you see in these trends of that. And it's kind of like, the antelope is usually, eats whatever they eat. I don't know what they eat, but it's sort of an observation of natural history. But I know from having done this before that one day, perhaps quite soon, those details that I kind of worked through somewhat carefully will turn out to be building blocks for the next thing one wants to do, for figuring out some bigger point or whatever else. So that's a very nice feature of rulology. It's something where it's so clean that it's not one of these things where it's like, oh, in a few years there'll be a different model and nobody will care. Or, in a few years there'll be a different way of doing measurements of this kind of biological system or something, and nobody will care about the thing that was done with in such painstaking way before. It's not the case. It's one of these things that has a sort of permanence of pure mathematics, a very fundamental kind of pure mathematics, but it's something that's also rather accessible. But it needs a slightly different mindset. It needs a kind of its own methodology of kind of defining very clean experiments, seeing how they come out, understanding principles of what's going on. In any case, it's a great field to get into because, as I say, among other things, it has this feature that sort of everything you do is a kind of solid brick that can be built on. Well, okay, so I spent most of the 1990s working on these kinds of things and understanding their applications to lots of areas. One of the areas that I kind of poked at was fundamental physics. And one of the things about these things like cellular automata is they kind of have already too much in them to be good models of fundamental physics. They have, there's this grid of cells that, you might say, well, maybe space is a lattice of cells. Well, it's not. We plainly know that it's not. And so it's kind of a non-starter if you try and say, well, let's try and model the universe with as a cellular automaton. That doesn't work out. Now, actually, something I've discovered only in recent years is a lot of people tried to do that in the early part of the 20th century. I mean, there's a long arc that leads to that. Back in antiquity, people were arguing forever about, is the universe discrete or continuous? Is it made of atoms, or does everything flow, or whatever else? That question was not resolved until the end of the 19th century. And at that time, people realized from both what had been done in chemistry and from observing Brownian motion and things like this, that there were discrete molecules. Matter was made of discrete things. And then it became clear you could think of light as being made of discrete photons. And then the obvious idea was space will be discrete as well. And so, sort of all the greats of physics in the beginning of the 20th century believed that space was discrete and tried to make models of it and so on, and it didn't work. And it didn't work because their model was something like a lattice. They couldn't make that consistent with relativity. And by 1930 or so, people gave up. And strangely, there's very little literature. I've been meaning to go do the history, go through the archives and so on, and find the notes that people had made about these things, but very little was published about it because it just didn't work. Well, then, we're close to a century later, and the interesting thing is we can make it work. And that sort of started in my efforts in the early 1990s, thinking about, well, what might the universe be made of? It's what might the sort of underlying data structure of the universe be? And what I started realizing is what one wants is the most flexible possible data structure. And I thought at that time about just sort of atoms of space that were connected, related by some kind of network. There were a bunch of technical issues with that. Sort of the mini breakthrough in 2018 was to realize that if you think about those relations as corresponding to a hypergraph, so you just say those atoms of space, all you can say about them is they are distinct, but they are related, they have these relations. And you can think about those relations as being, there's four atoms of space that are related. Well, you can represent that as a hyperedge in a hypergraph. If it was just two atoms of space that were related, you could represent that with an ordinary graph. But if you can have larger numbers of atoms of space that are related, you can represent that with a hypergraph. And so then the idea is kind of that the sort of most flexible data structure one can come up with, and we keep on coming back to this data structure, by the way, is this idea of a hypergraph, just a bunch of discrete elements with relations between them. Well, so the idea is then, what if everything that's in the universe is just this giant hypergraph with all these relations between these atoms of space? And then, well, what happens to this universe? What does it do? Well, the idea is that what it does is it gets updated by some rule, some rewrite rule for these hypergraphs. A little bit like the rewrite rule you see in a cellular automaton, but now it's saying when you see a sub-hypergraph that looks like this, rewrite it into one that looks like that. And so then the question that you can ask is, so one feature of that is, in this model, space is a very different kind of thing from time. And you might say, well, that's hopeless. We know space and time are intimately related in relativity and so on. Yes, that's true. But that turns out to be something that is emergent, not something you should burn into the foundations of the model. Now, I will say that the progression of time is the progressive computation of the successive states of the universe by the rewriting of this hypergraph into a different hypergraph and so on. So then the next question is, well, okay, we know that if you have a bunch of molecules, for example, actual physical molecules, and they're bouncing around and so on, and we know that the large-scale limit of a bunch of molecules bouncing around is a gas. And gases have certain continuum properties. We know that certain continuum equations, we can look at the equations of fluid mechanics, the Navier-Stokes equations, that's what emerges, pretty much independent of the details of what the shapes of the molecules are and their interaction laws and so on. You still get the Navier-Stokes equations. So then the obvious question is, well, what do you get if you look at this hypergraph rewriting system and you say, what's the continuum limit of lots of hypergraph rewriting going on? Well, the thing that I had figured out a part of, at least in the 1990s, is the thing you get is the Einstein equations. So, and we figured out a lot more about that in 2020, that the sort of large-scale limit of hypergraph rewriting, with a bunch of footnotes, which we should talk about, with a bunch of footnotes, the sort of continuum limit of hypergraph rewriting is the Einstein equations. So that's saying that if what's underneath everything is this hypergraph and which is being rewritten, then what you will see on a large scale is sort of the continuum behavior is what we know is that way from general relativity and from what we know from physics from the 20th century. So now tightening up that idea that the limit of hypergraph rewriting is the Einstein equations and so on, that's a lot of work. You have to invent a lot of math to do that. We have a big project that we're calling infrageometry, which is the attempt to invent all that math. And when you think about sort of space as it's normally thought about, it's a manifold. A manifold microscopically is kind of little patches of Euclidean space. But in the case of our hypergraph, microscopically, it isn't patches of Euclidean space, it's a hypergraph. And the question is, what is the geometry that you can construct, the analog of geometry that you can construct from the limit of hypergraphs that's different from what you get in standard differential geometry from sort of the limit of Euclidean space? And we've made quite a bit of progress on this, and there's a lot that one can kind of say, there's a lot that we were able to say even in 2020 about this, but there's a lot of mathematical tightening that we want to do, and that's one of the big projects we're in the middle of right now and could do with any help we can get on. But kind of well, let me give you one sort of indication of an idea. The thing that one of the issues, you got this hypergraph. You say it's going to limit somehow to space. Well, one question is, what dimensional space? It's just a graph. It doesn't know anything about the dimensionality of space. Well, so the dimensionality of space has to be an emergent feature of this graph. And so how do you even work out what effective dimensionality a graph has? Well, you can start from one node in the graph, and you can go to all nodes that are connected by one edge, two edges, three edges. You can build up this kind of ball where you're building it up, R edges. You go out and you ask the question, how many nodes in the graph do you reach when you've gone out R steps in graph distance from that node? Say, well, if that number of nodes grows like R to the D, that's like having a sphere, a hypersphere with volume, with a volume that goes like R to the D, so it's like a D-dimensional hypersphere. So that's a way you can take this graph and just sort of probe the graph to say, what effective dimension does this graph have? Now, one of the features of our models is we expect that the number of dimensions doesn't have to be an integer. So then the question is, well, how do you build, for example, differential geometry in this kind of fractional dimensional space? It's not like a fractal because those get embedded in integer dimensional spaces. It's something different. It's a truly intrinsically fractional dimensional space. How do you build an analog of differential geometry and work out curvature tensors and all this kind of thing in that setting? And we've got a fair distance with that, in fact. But it also has an interesting feature that this idea of dimension fluctuations, the universe isn't precisely two-dimensional, is something which is a kind of a prediction of our model. We don't know how big these fluctuations will be. Did they survive to the time of the cosmic microwave background or not, or whatever else? But that's a thing that, independent of how big the elementary length is, independent of what the length scale of microscopic structure of the universe is, that's something we don't even need to know about that scale. There's sort of a scale-independent prediction that there'll be dimension fluctuations somewhere. We don't know how big, et cetera, et cetera, et cetera. So then an interesting question which we're trying to pursue is, how would you detect a dimension fluctuation? What astrophysical experiments could you do to predict that, and so on? So in any case, sort of the first branch of what's going on is you've got this hypergraph, you're rewriting this hypergraph, you are trying to understand the limit of that, you're trying to understand that mathematically, physically. The sort of the big excitement is that it gives you kind of general relativity and the structure of space-time, but with some extra pieces that aren't part of general relativity. And, one of the things that is interesting is, what is the macroscopic effect of the microscopic structure of space? And you could ask the same question for matter. What is the macroscopic effect of the microscopic structure of matter, the atomic structure of matter? Well, one very big macroscopic effect is heat. Heat is the motions of these microscopic particles in matter. It's a phenomenon that is a macroscopic phenomenon, that is a shadow, something that comes from microscopic structure of matter. So an interesting question that I'd love to know the answer to is, what is the macroscopic manifestation, if there is one, of the microscopic discreteness of space? And I have a guess that dark matter might be very misnamed and not be matter at all, and actually be a feature of the microscopic structure of space. But that would be a very exciting thing to be able to show. We're working in that direction, and one of the things that's a current project is making very efficient hypergraph rewriting code that can let us get a large distance in this hypergraph rewriting process to be able to see kind of features of what will it mean if you have, a galaxy's worth of matter producing of energy momentum, basically. What does that really produce in our models, and what kind of features does that have? And does it really follow, Newtonian type gravity or relativity or whatever, or not? Okay, so that's one kind of thing. Then in physics, the next big sort of direction has to do with quantum mechanics. And I've talked about how, you have this hypergraph and it's being rewritten according to these rules. One of the important points is, all you're told is you've got a hypergraph and you've got a rule. There turn out to be many places in principle you can apply that rule. And so you can build up this kind of multi-way graph of the results of all sorts of different sequences of rule applications. So it turns out one of the things we've been studying a lot in the last few years is multi-way graphs. I kind of invented that idea back in the beginning of the 90s when I was working on new kind of science. But I didn't really develop it properly at that time. But multi-way graphs show up all over the place. And for example, let's say you're playing tic-tac-toe and you want to know, what are all the possible moves you can make in the game? We have a game graph. You can think about that game graph as a multi-way graph in which all the different possible moves that you can make are set out in that graph, and every particular game is a path through the multi-way graph. We'll also talk about how you can multi-way graphs are kind of what you get when you work out the consequences of mathematical axioms. They're what you get if you think about sort of aggregating if you think about a lot of things where people say that's a random process. You can say, well, what's the multi-way graph that represents all the possibilities for what can happen in that random process? And the whole point is that there are general things you can start to say about multi-way graphs. The most significant is what we call branchial space. So you have this multi-way graph, it's branching in all these different ways. You've got all these separate branches, all these different threads of history. And the question is, what's the relation between the threads of history? So you make a slice through this graph, and there are all these dangling ends that are different threads of history. So one thing you can then do is to say, let's look at threads of history that have a common ancestor, let's say even just one step back, and let's make an edge, join them in a graph. What you get from that graph is what we call a branchial graph. That graph is essentially a map of these different threads of history. And that branchial graph is important in lots of different cases. I should have mentioned another thing. We got lots of kinds of graphs, and conventionally in all the things we write, they all have different colors. So these hypergraphs, they've got blue edges. The branchial graphs have purple edges, a kind of a pinkish purple edges. There's another kind of graph that's very important, and that's causal graphs. So when we do this updating of our hypergraph, there are a sequence of updating events. Every time we do an update, it's an event. And that event, the output from that event, you can think about it as applying a function. The output from that function is other stuff that will then get used as input to future functions. And so you can draw a kind of a causal graph that represents the causal relationships between those updating events. And so the events, the sort of the carrier of all those events is this hypergraph, or it might be another kind of system. You can make causal graphs for lots of kinds of systems, but the carrier is this underlying data structure, but then you're generating this causal graph of the relations between all these events. And that causal graph in many ways is more fundamental than the hypergraph. The hypergraph represents the sort of instantaneous structure of space. The causal graph represents the progression of time in space, so to speak. And what you end up doing is, from that causal graph, you make slices through the causal graph at a fixed, what you consider to be a fixed time. you make what in the language of general relativity would be called space-like hypersurfaces. You make surfaces that correspond to this is the thing that we'll say is the state of space at a certain moment in time. It's a simultaneity surface in the language of relativity. And so what you're doing is you're making these, from this causal graph, you can make many different simultaneity surfaces. Those correspond to different reference frames in relativity. But this causal graph is an important kind of construct. Actually, the causal graph, you can make a multi-way causal graph. In an ordinary causal graph, you've got, in the language of physics, every event is at the top of a light cone. The light cone, the edges of from the causal graph are light-like edges. They are just as a matter of the way we've set up units. Those are edges that effectively go at the speed of light. They take one elementary time to go from one event to the next. They travel one elementary length to go from one event to the next. So they kind of define. So there's, and normally you have these little light cones. If you're looking at a single thread of history, you have sort of ordinary light cones that relate different events by the fact that they have a common ancestor in some in physical space. Well, it turns out there's also a notion of that you can make this multi-way causal graph in which different causal edges can be related not by space-like separation in physical space, but by branch-like separation corresponding to different paths of history. And so that's sort of the big object is the multi-way causal graph, which has one direction of it, one slice through it is a reconstruction of space. Another slice through it is a reconstruction of different paths of history. And sort of the big idea then is that's what quantum mechanics corresponds to. Quantum mechanics is a story of all of these different branches, all these different threads of history. And it's kind of it starts with something a little bit like the many worlds interpretation of quantum mechanics, but we have a very different story. Because our systems are discrete, something which was kind of missed, I think, in thinking about the many worlds interpretation is that not only do you have branching of different paths of history, but you also have merging. If you are dealing with continuous systems, the chance of two branches merging is basically zero. But if you're dealing with a discrete system, the branches merge all the time. And that branching and merging is what gives you kind of the really rich structure of multi-way graphs and the really rich structure of branchial space. And kind of the sort of proto-conclusion, which we would like to tighten up a lot more, is in physical space, when you make the sort of slice into physical space, well, in that case, we know that we're following the Einstein equations, and you can, and that determines things like the paths of geodesics and the sort of the force of gravity associated with the deflection of those paths of geodesics and so on, those shortest paths. Well, what appears to be the case is that the exact same phenomena, the exact same kind of abstract setup that in physical space leads to general relativity, in branchial space leads to quantum mechanics and quantum field theory. So the basic picture is what the presence of energy momentum. I should say what energy momentum is in these models. Energy momentum is basically a flux of causal edges. It's basically the amount of activity in the network is sort of a bulk measure of energy in these models. And so in any case, the thing that the point is that what you find is that the presence of activity in the network, effectively, energy momentum, interpreted as energy momentum, deflects shortest paths in the network. And that's kind of what leads to gravity in physical space. Well, in branchial space, we think that we can identify branchial space essentially with quantum phase, and then the deflection of paths in branchial space corresponds to a change of phase, and the deflection of paths as a result of energy momentum in sort of the formulation of quantum mechanics from the path integral. The path integral says e to the I times the action. The action is basically a relativistically invariant version of energy density, the integral of that. The presence of that energy momentum changes the quantum phase. And that's saying effectively that you're deflecting paths now in branchial space. So the claim is that the path integral is in branchial space what the Einstein equations are in physical space. That's a rather lovely kind of conclusion. Also, there's been a lot that's been believed since the 1990s about the ADS-CFT correspondence, the holographic principles of correspondence between kind of things in general relativity, things in quantum field theory. In our models, that there's much to tighten up around this, but that seems to be it's all the multi-way causal graph. You're seeing two different projections of the multi-way causal graph. Those are the CFT side is the branchial projection, the ADS side is the spacelight projection. So in any case, there's that's kind of a little bit on sort of how fundamental physics might work out there. One of our big initiatives right now is infrageometry, trying to tighten up the mathematical formulation of these kinds of things. Another direction is an effort to understand quantum field theory, and the thing that in quantum field theory, sort of a method of calculation is Feynman diagrams. I used to know Dick Feynman fairly well, and one of the things he would often say is, Feynman diagrams are a stupid way to compute things in quantum field theory, but we haven't come up with any better ones, so that's what we're stuck with right now. Well, Feynman diagrams are these diagrams that represent sort of the in thought about in space-time, the sort of you have an interaction like an electron could interact with a photon or something like that. There's a vertex in the Feynman diagram that represents that interaction. What I realized recently is that Feynman diagrams are basically causal graphs. They represent the lines in Feynman diagrams are basically causal edges that represent the causal relations between these interaction events. Well, one of the things I've also been, there's a question of what are particles in our model of physics. We think qualitatively there's some kind of topologically stable structures in this hypergraph. A little bit like an eddy in a fluid, there's some kind of topologically stable sort of knot in the hypergraph that can be that can represent a particle. We don't know how that works. Now, I was kind of feeling really bad about that until I realized that in quantum field theory, we don't really know what particles are either. In quantum field theory, you say, what's a proton in quantum field theory? Oh my gosh, it's a very complicated thing. We don't know how that works. What quantum field theory tends to do is to say, we have these incoming particles represented as plane waves coming in from infinity. Eventually, they interact with other particles represented as plane waves, and then things go out, and we figure out the S matrix, the scattering matrix associated with the incoming and outgoing features, and that scattering matrix in certain limits can be worked out using Feynman diagrams. And so I realized that we have the same setup. Our causal graph is like a sub-Feynman diagram. That is something that is actually mixing the structure of space and our kind of concept of particles. But by the way, I should say that in thinking about how a hypergraph's limits to space and so on, what we imagine is that this hypergraph at a mathematical level is limiting to something more like a fiber bundle, where there's a base that represents that is this sort of non-compact thing that represents the structure of space. And there are these little fibers that are compact kinds of things that might have the structure of groups, Lie groups, for example, that and that we can decompose the hypergraph into this, compact and non-compact pieces, and that will correspond to physical space and the internal degrees of freedom associated with gauge theories and so on. But in any case, the point is that what I realized recently is that you don't need particles to do particle physics. And in fact, Feynman diagrams and the whole way one deals with S matrices, one doesn't really have big fluffy particles like protons. One just has these very simple concepts that are the things that are supposed to deal with what in traditional physics have been thought of as point particles, because we just don't know anything about their structure. Anyway, so another initiative is to try and understand this kind of sub-quantum field theory. A lot of interesting concepts there, notions like subtime, where you have loops in the causal graph that lead to closed time-like curves, where you can sort of do micro time travel, so to speak, except you can't fit anything through there. It's just something that's part of the structure of space-time. But but the guess that those are associated with the actual loops that you see in Feynman diagrams and so on. So a lot of interesting things there which need to be worked out. So, okay, so that's a little bit on some fundamental physics. I said that this kind of general paradigm of, well, things like multi-way graphs, this idea, I should say another thing about physics before we go on to other things. One of the things that's sort of a mystery from this whole picture of physics is, okay, you say, well, maybe there's some simple rule that will give us current physics. We already know from things like fluid dynamics that it's not going to matter that much what the details of that rule are. We're always going to get certain continuum features. But some things about the universe might depend in detail on that underlying rule. And so the question then is, well, why did our universe get rule number blah, 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 not some other rule? And that's a very confusing thing at first. Why would we get, for example, let's say a simple rule as opposed to a more complicated rule? Why did we get dealt the simple rule, so to speak? And what I realized at some point was that actually the way to think about this is, just as we've said that quantum mechanics emerges by looking at all these different paths of history, so also we can just say, well, what if the universe just followed all possible rules? We get something which is kind of this object that is the result of following all possible computational rules from all possible initial conditions in all ways. You might say, well, there's nothing you can say about that. But actually, that object has a huge amount of structure, because let's say you're dealing with Turing machines as your basis for studying that object. You have two Turing machines. They use two different rules. They go off to two different states. But later on, those two states might merge into the same state when you apply different rules. So you have this very complicated branching and merging kind of structure. I call this whole object that is the kind of entangled limit of all possible computations, the Ruliad. And the Ruliad is a unique object. There's only, given the idea of computation, it is a necessary, abstract, unique object. And so then the question is, well, you have this Ruliad object. You can start studying the properties of the Ruliad. I've done that a bit. There's a lot more that can be figured out. In a sense, rulology is the study of little pieces of the Ruliad. But then the question is, well, in the Ruliad, how do we get physics out of the Ruliad? And what we realize is observers are also embedded in the Ruliad. So what we're asking is, how does an observer aggregate detailed features of the Ruliad to conclude things about what their perceived physics is? And the big claim is that observers like us inevitably observe the laws of physics that we observe. So what's an observer like us? Well, inside the Ruliad, there's all these computations going on, all these irreducible computations. But we are pretty simple observers. We are computationally bounded observers. We don't get to do as much computation as the universe does. We have a limit to the amount of computation we do. In fact, it seems like a lot of what our brains manage to do is to take lots of different inputs, megapixels of visual data and so on, and then what we do is crunch that down to something where we get a sort of single thread of action that comes out of that. Every tenth of a second or something, we're like, what do we do next? And so we're sort of taking, we're not doing general computations. We're doing very particular computations where we're sort of taking the world as we perceive it and then trying to deduce what we should do based on that. And one of the things, so we are doing very bounded kinds of computations. We also have another feature, which is we believe we're persistent in time. Even though we might be made of different atoms of space at every moment in time, we think it's the same us going through time. We believe we're persistent in time. We believe we have a single thread of experience through time. So those two features, computational boundedness and the belief in having a single thread of experience, it turns out those two features are sort of applied to the Ruliad, eventually give you, it seems, the laws of physics that we know. So it is a philosophically rather interesting thing that we are sort of in a position to derive the laws of physics. Actually, the simplest case to see that in is the second law of thermodynamics. That's kind of the third branch of achievements of 20th century physics: general relativity, quantum mechanics, statistical mechanics. The second law of thermodynamics, invented in the 1800s, is the idea that, you start these gas molecules off in some configuration. Chances are they'll end up in a configuration that we just describe as random. So we have the constraint, all the molecules are in the box, but we say chances are that the configuration of molecules will be something where we just have to say it looks random. And therefore we have to say its entropy has increased. The number of states of the system consistent with what we know about it has increased. Though it's been very confusing how that works, because after all, given any particular state of a system, if the laws of mechanics are reversible, you can go back and figure out the initial condition. So how come there is this sort of irreversible tendency towards randomness? I started thinking about that question 50 years ago now, and I think I finally have a pretty good story about how it works. And it all has to do with computational irreducibility. It has to do with the fact that the laws of mechanics, while they are reversible, are doing irreducible computation. That what those gas molecules, which at the beginning were in some simple configuration, an irreducible computation is done, which kind of scrambles them up. It's like you're encrypting the initial data about these molecules, and the result is something that you can't decrypt except by doing an irreducible amount of computation. But if we are computationally bounded observers, we can't do that. So to us, we just have to sort of throw up our hands and say, looks random to us. So that's the story of the second law of thermodynamics, is a story of the interplay between computational irreducibility and our computational boundedness as observers. We believe in the second law because we can't see any better because of that computational irreducibility. If we were not computationally bounded, we wouldn't believe in the second law. We would just say, yeah, it's some configuration of gas molecules and it evolves and now we've got another configuration. We wouldn't say, we can't characterize that configuration. It just looks random to us. So that's an example of how the nature of us as observers implies a law of physics. And the claim is the same thing happens for general relativity and for quantum mechanics, that our nature of observers played against the Ruliad inevitably gives us the reality that we perceive. And to other observers, you would have a different reality. But this means that it's something that is, as I say, rather philosophically interesting, that you can imagine, that you can derive the laws of physics. Well, okay, so let's keep going. Another thing you can think about is mathematics. What is mathematics? People 100 years ago I might say, by the way, that I think in the arc of scientific history, what happened 100 years ago was formalization really became a thing. In physics, in mathematics, even in biology, the idea that you could sort of formalize things in some abstract way was something that really, really arrived. But that formalization eventually led to the idea of computation. But that formalization it figured things out that were essentially computations. And the thing was that a lot wasn't known about how computation works. Computation in bulk in the wild had not been studied. Nobody had a computer. You couldn't do it. So if somebody said, well, there's this formalization in math, but we can't work out the bulk consequences of this because we don't have computers to do it. And I guess that I was lucky to kind of come along at a time when, yes, you could do that. You could look at computation in bulk, and then probably my big idea was you could look at computation in the wild, not programs that we very carefully wrote, but just what's everything that's out there in the computational universe. And what you realize is there's all this new intuition, all these new phenomena that come in when you think about computation in bulk, computation in the wild. And those are the things that allow you to take the things that have been figured out at the beginning of the 20th century in all these different areas and make further progress on them, because you can say something about that formalism now in bulk in the wild. So mathematics is another example. So the kind of Hilbert program of mathematics, take mathematics and kind of grind it down to something, to fundamental elements from which you could kind of mechanically build up all the mathematics. That kind of got a bump with Gödel's theorem, which was kind of the first example. Gödel's theorem was one of the discoveries of universal computation. In the case of Gödel, that arithmetic could do universal computation. But not the way he put it. That was a later description, but that was what it amounted to. So In any case, so we have this picture of mathematics as something where you can grind down to primitives and then build up to all of mathematics. You can start off with the axioms and prove all the theorems of mathematics. Obviously, in building Wolfram language and Mathematica, one of the original motivations had to do with being able to do that for math and generalizations of math. So that was sort of a computational, this idea of symbolic expressions and transformations of symbolic expressions was my version of kind of the way to think about sort of what is the foundations of math and beyond, so to speak. And it's worked out really well, remarkably well over 45 years now. That's been the infrastructure on which we've been able to build everything that Wolfram language can do. It is sort of ironic that the model for the universe involving the sort of hypergraph rewriting is very much like transformations to symbolic expressions, although it's a bit more general than the kind of transformations we've been doing with tree-like expressions. And that's one of the sort of frontiers for things, is thinking about kind of hypergraphs as a foundation rather than trees. In any case, the thing that, so thinking about mathematics, you start from a bunch of axioms, you prove a bunch of theorems. You can get this giant network of what theorems you can prove from what axioms and so on. And then the question is, well, actually, if you think about what are all the possible axioms you could use for mathematics, what is the structure of the network that you get from all possible axioms? Well, it turns out it is exactly the Ruliad. So in a sense, the foundation of all possible mathematics is the same as the claim of the foundation of physics. It's the Ruliad. And so the question is, well, physical observers perceive the Ruliad in ways that lead to general relativity and so on. What do mathematical observers, how do mathematical observers perceive the Ruliad? And what are mathematical observers doing? They're basically saying, we're going to pick up certain theorems, certain sort of atoms of existence. That's sort of the generalization of an atom of space in the Ruliad. We're going to pick up certain atoms of existence, which in this case we interpret as theorems. We're going to pick up some atoms of existence, and we're going to say, we believe these atoms of existence. These are theorems or axioms that are true. We're going to put them in a bag. We're going to say, okay, given those, what is the entailment cone, the analog of the light cone? What are the consequences of these axioms? Well, in a sense, that's sort of a picture of what's happening in mathematics. The question is sort of what do human mathematicians perceive in this whole structure of the Ruliad? And so one question is this: how hard is it to do mathematics? It could be the case that every time you do geometry, every time you talk about Pythagorean theorem, you have to be going and recursing down and saying, and this is my definition of real numbers, and this is how I'm doing, and you're going all the way down to the lowest level axioms. This is how I define a number, et cetera, et cetera, et cetera. But we know that, in fact, you can do mathematics at a much higher level. You can do it just in terms of, geometry. You can talk about angles and things like this. And you don't have to always think about, well, what's the definition of the real numbers that I'm using to specify the measure of this angle or whatever else. And that fact, I think, is the direct analog for metamathematics of what happens in physics in, for example, the second law of thermodynamics or fluid dynamics. When you do fluid dynamics, you can just think about a fluid at the level of being a fluid that flows. You're not always recursing down and saying, oh, and I need to know how the molecules are interacting. You just say, here is this fluid velocity. I can work out things at that high sort of fluid dynamics level. I think that's what's happening in mathematics, that mathematicians actually do. And I think that's one of the reasons that things like Gödel's theorem have not been more important in mathematics, because in practice, the sort of Gödel's theorem is relevant at the level of the molecular dynamics. It's not relevant at the fluid dynamics level. It's been kind of smeared out at the fluid dynamics level. And most of mathematics is operating at that fluid dynamics level. Occasionally, it'll be like hypersonic flow. You'll have some shock that reveals kind of the discreteness, that reveals the underlying axiomatic structure of mathematics and reveals things like Gödel's theorem and so on. I mean, one of the things that's notable in rulology and computational irreducibility is kind of visible at every turn. And the limit of computational irreducibility is undecidability. In mathematics, the story of most of the mathematics that has been done is the finding of pockets of reducibility within the Ruliad. one feature of a computationally irreducible system is there are always an infinite number of pockets of computational reducibility to be found within that computationally irreducible system. And the story of what we discover, whether it's our laws of physics or our laws of mathematics, is we are finding those pockets of reducibility. There are many analogies you can make between metamathematics and physics. Here's a funky one. What is a black hole in physics is like a decidable theory in metamathematics. A decidable theory is a theory in which there are no infinite proofs, in a sense. You can bound the length of proofs. And so, a black hole, at least in the simplest case, is a piece of space where every geodesic path, every sort of space, every world line eventually crashes into the singularity in the center of the black hole. And so that means that time is finite. Every path is a finite length. And that's the direct analog of every proof being a finite length. I mean, there's more detail to this, but that's kind of the basic idea. So it's kind of a correspondence between sort of what you think about in physics and what you think about in metamathematics. So, and there are other things, like here's another one. The homogeneity of physical space and the possibility of pure motion, the possibility you can take an object and move it somewhere else, that's something that's not obvious in our models. That it's not obvious that you can just take that thing and, like an eddy in a fluid or something, even though it's made of different atoms of space, it's still kind of the same thing at the other end. That you have to derive the possibility of motion in physical space. Then you ask the question, well, what's motion in metamathematical space? Well, what that is really taking a different point of view about mathematics. It's like, you've got the algebra point where you're thinking about mathematics in algebraic terms. You've got the geometry point where you're thinking about it in terms of geometry. That's like taking a different point of view in physical space. And I think that the homogeneity of, if in the Ruliad, there is a certain inevitable homogeneity to metamathematical space. And I think that homogeneity of mathematical space is the reason that there are correspondences, dualities between different areas of mathematics. Because essentially what's happening is it is inevitable that there is sort of pure motion in mathematical space. And that means this thing you did over here in arithmetic, or in algebra or something, you can transport that to geometry, just like you can transport, a physical object from one place in physical space to another. So that's a little bit on kind of mathematics. You can think about questions like, what's the infinite time limit of mathematics? We've proved a few million theorems in the literature of mathematics so far. What's the infinite time limit? How do we stake out what parts of that are of human interest, so to speak? What parts are we going to say, yeah, that's an interesting piece of mathematics, rather than just, that's a random theorem we don't care about? Well, okay. So just to cover a couple of the other things that we've been making some progress on, another big area is biology. And biology is, again, a story, it turns out, of rulology, computational irreducibility, etc. And sort of the big idea there is, let me show you at least one picture if I can find it. So the idea is we're going to make a minimal model for biology, and this is how it works. So this is just a solid automaton rule, and that's the genome. That is just a simple rule, and that's what that genome does when you let the organism grow, so to speak. And the idea is we think about mutations to that genome, just single point mutations to that genome. And what we're going to do is we're going to say, let's make single point mutations to that genome, and let's try and find genomes that lead to organisms that live longer before they die out. Let's say that's our fitness criterion. Well, so most organisms, most tries that we make by mutating the genome won't lead to progress. And that's all the red dots in this picture. But occasionally there'll be a breakthrough and we'll get sort of a longer lived organism. And so that's what happens here. We start from just this very null organism, and we end up with this organism that lives for some number of steps here. This is sort of a picture, an idealization of biological evolution. And if you roll the dice a different way, you'll get a different sequence of kind of breakthrough organisms, so to speak. And I kind of view this as being a little bit like what we see in the fossil record. We're kind of building on a discovery that got made to kind of build fitter organisms and so on. Well, you can do a lot of things with this. You can, one of the things we're thinking about right now is kind of how do we think about, it's clear that there are different discoveries that are getting made in these different branches of history, in these different possible kind of evolution paths. But how do we characterize those discoveries? How do we characterize the kind of mesoscale structure of these organisms? It's kind of like we discovered how to make a mitochondrion, and then we make use of that. We discovered how to make this kind of organ or something, then we make use of that. We'd like to characterize that. That's one of the things we're thinking about in theoretical biology right now, is the characterization of kind of these structures and how one builds on one set of discoveries to get to the next level to go on from there. Now, you can do things like you can make multi-way graphs of all possible paths of evolution, and there are lots of things you can say from that. One of the things that you can realize from these multi-way graphs is there are all possible mutations you can make in this in the genomes of these idealized organisms. And the question is, so what you're effectively doing is you're taking the set of all possible mutations, you're kind of building up the Ruliad from all these possible mutations. But now the fitness criteria that you're giving in that the environment of the world is giving to these organisms is making slices of saying, this is a set of organisms that are fitter than those organisms, and so on. You're kind of defining a kind of, it's like the space-like surfaces we talked about in space-time and so on. You're defining this series of kind of fitness surfaces that are getting progressively fitter organisms. And so then the big question is, well, what is that slicing? How is that slicing done by the actual kind of environment of the world? And the big claim is that slicing is done in a computationally bounded way. In other words, there's all this underlying computation going on, full of computational irreducibility. But when it comes to will the organism live or die, that's a pretty fuzzy thing. And, a way to think about it is when the organism is born, it doesn't immediately have to be able to generate 1,000 digits of pi. The organism has to be able to roughly do this kind of thing and manage to figure out how to walk and eat and fly and whatever else it's doing. But it's not something that is a computationally complicated thing to do. And we're kind of learning with the advance of AI how computationally not really complicated a lot of the things that we end up doing actually are. So in any case, the way to think about, so one question is, why does natural selection, why does it make progress? Why does it work? And the claim is it works for the same reason that we have laws of physics, the same reason we can do mathematics, high-level mathematics. It works because the environment of the world is imposing computationally bounded fitness criteria, which are allowing us to kind of navigate through this multi-way graph to get to fitter organisms. So in a sense, the statement is the biological evolution works because we have a computationally bounded observer in the form of the environment acting on this computationally irreducible underlying dynamics. And that can lead to kind of that leads to the success of biological evolution. Now, a question is, well, what kind of things, what are the laws of biology analogous to the laws of physics that emerge from that observation? And we made some progress on that very recently. And it all has to do with this thing we call the Ruliad ensemble. So here's kind of the question. So it starts from the question of what is biological matter? We've got molecules in biology, we've got molecules in liquids, but, the gooey stuff that's inside all of us isn't much like a liquid. It's not just molecules bouncing around at random. Instead, what molecular biology has discovered is that it's really molecules that are kind of that are orchestrated in what they do. This protein binds to this one, which moves this piece to that, and then it binds to this, and it's all a big piece of sort of bulk orchestration. So the question is, what's the theory of bulk orchestration? For something like molecules in a gas, we know that we have bulk theories like fluid mechanics and so on. What is the bulk theory of biological matter? So the thing one realizes is, imagine that you've got all possible rules. you're picking rules at random for how things work in your idealized biological system. But actually, those don't make it. The rules picked at random aren't going to be the ones that survive in a computationally bounded fitness criterion. Instead, there will be some set of rules, we can call it the Ruliad ensemble, of possible rules that kind of are the results of some computationally bounded fitness criterion. We don't necessarily say what that fitness criterion is, we're just saying it's computationally bounded. Okay, so the big kind of discovery recently was just saying the fitness criterion is computationally bounded tells you things about this Ruliad ensemble. It tells you things about what can happen in these rules, which on the top, at the large scale, the whole organism is subject to natural selection. But down inside, there are these rules that are doing what they do. The point is that even without knowing in detail, oh, you need to have a longer beak in order to survive in this case or something like this, you don't need to know that stuff. You just need to know there is a computationally bounded fitness criterion. That has consequences for the microscopic structure of these rules. In particular, it leads to the presence of what we call mechanoidal behavior that seems to have small-scale mechanism in it. It's very similar to this thing I was mentioning of these structures that are kind of like organ-like structures or something. It's microscopic kind of mechanism. The whole system is full of computational irreducibility, but there are pockets of reducibility, and the imposition of this large-scale fitness criterion seems to inevitably lead to the presence of this kind of mechanoidal structure, these sort of visible pockets of computational reducibility. We haven't figured out the whole story of what this means, but that's kind of the beginning of having a theory of bulk orchestration, just like statistical mechanics is a theory of bulk processes that are going on with molecules. So that's kind of a direction in biology. There are other directions we're interested in about origin of life and things like this, lots of other things there. And sort of the challenge in biology is to have models that are simple enough that you can make serious conclusions from them, and you don't just put in the kitchen sink into the models. You don't say, oh, we're going to have a, sexually reproducing organism that's going to have this, a mortality curve, and et cetera, et cetera, et cetera. Pretty soon, it sort of becomes a self-fulfilling prophecy that you'll reproduce certain features of biology because you put all those things in. What we're interested in is what are the true sort of foundational elements. And I think what we're discovering is biology and a lot of the phenomena of biology are fundamentally computational phenomena. And they're phenomena that don't depend on all those details about DNA or whatever else. They're phenomena that are just a consequence of sort of the computational structure, the kind of rulological structure of biology. Well, okay, there are other places you can apply this. So another one is in machine learning. They're interested in sort of what's the minimal model of machine learning, have a very simple model that's actually a kind of a cellular automaton-like thing, where instead of having weights in a neural net, you're just saying you're using rule A or rule B at this point in this lattice. And you can do all sorts of learning type things, sort of simple versions of what neural nets do. But what you see there is that what's happening in the training of those kinds of idealized sort of discretized neural nets is you're picking up kind of lumps of computational irreducibility and figuring out how to put them together to achieve the training criteria you want. It's very similar to biology. We can think of biology as putting together lumps of computational irreducibility and assembling them to actually achieve the fitness criteria that we want in biology. Well, so that's the picture of machine learning. One thing that tells one is that, it's as if kind of the analogy is you're trying to achieve a criterion. You're trying to build a wall, for example. You could do that by engineering it with nice shaped bricks. Or you can just pick up random rocks off the ground that are different shapes and assemble them to make that wall. It's that second thing that's happening in machine learning. You're picking up these lumps of irreducible computation and assembling them to get the results you want. And that process, among other things, if you say, well, why did the rocks assemble that way? There's no real answer to that. It's just because this particular rock happened to be lying around, and that's what we picked up in our wall construction or our training process in machine learning. So it kind of tells one that sort of the goal of sort of getting the big arc of explainability in machine learning isn't really there. there will be laws of machine learning. We don't know what they are. It'd be a very interesting thing to try and find them. Just as there are laws of physics, there are laws of biology that we're trying to find. What are the kind of emergent laws? What's the analog of the Ruliad ensemble in machine learning? We don't know the answer to that yet, but that's an interesting question to ask. And, what kind of, what is their mechanoidal behavior in machine learning? Is that what the computationally bounded fitness criteria that we have in machine learning lead to? So again, we've got the situation that the things we want the machine learning to do, whether it's generating language in LLM or whatever else, are very computationally simple compared to the full computational ability of the system. And that's something that we plainly see in all of the computational effort that it takes to train machine learning systems and so on. Well, okay, there are other things in theoretical computer science. Thing we're just looking at was the P versus NP question and the rulological formulation of that question, which is just look at a bunch of Turing machines and see within a certain domain of Turing machines of a certain size, for example, there are deterministic ones. You see what they can compute. There are non-deterministic ones, which are essentially multi-way Turing machines. What do they compute? What's the comparison between computation speeds in those different kinds of systems? And we got a bunch of results on that, which make it clear that the P versus NP problem is a lot squigglier than you might have imagined. It's the kind of thing where it's kind of really picking at undercitability and incompleteness and so on. It's not just and somebody will find a great piece of math and just prove it one day. It's a much more complicated story than that. And you start to see that by analyzing it in a kind of rulological way. So there are other fields that we're interested in. Economics is another one I've been interested in trying to learn more about. Actually made a little bit of progress just a few weeks ago in a somewhat plausible model for economics. I think the big picture is that what I suspect is the case is that value in economic systems is essentially the discovery of pockets of computational reducibility. It is the ability to kind of jump ahead, to use that assembled iPhone rather than mine all the pieces and put it together for yourself. It's the ability to kind of have that jumped ahead thing that is sort of the value that progressively increases in the world. And the reason I think that is the sort of fundamental value is because, well, we all have finite lives, and so it matters to get something now rather than after 10,000 years of foraging the components, so to speak. That's the beginning of a story that I'm trying to find sort of what are the minimal models of economics that we can then do, like our minimal models of biology, to try and see a bunch of the phenomena of economics emerge from those models. I think there are also things one could do in neuroscience, in linguistics, probably in more general social science. One of the questions in social science is, why is history possible? We've got 8 billion people all doing their own thing, and yet we think that there is a story about what happened historically. People may disagree about the details, but there is some coherence to that story. And that's the same type of thing as the observation that, there's fluid dynamics, not just a bunch of molecules randomly bouncing around. Well, okay, so that's a little bit on some of the things we're up to, and I've probably forgotten some key areas, but that's a quick kind of romp through different kinds of things we're doing. I think the thing I want to say is that there's what can you get out of this winter school from all of this? I think there's intuition, there's methodology, there's specific results and approaches. About intuition, you've got to get the intuition of computational irreducibility. People don't have it. You constantly see people say, oh, you've got this complicated thing. We'll have to make a very complicated model of that. It's just not true. But you only get to know that when you've actually experienced computational irreducibility for yourself. Do some computer experiments. Actually make that hypothesis for yourself. I know what's going to happen. Then run it and be embarrassed, as I constantly am, that the system did something you didn't expect. I mean, my kind of whimsical version of this is the computational animals are always smarter than we are. It's probably, we should say, from the principle of computational equivalence, they're always at least as smart as we are. But in any case, they always do things you don't expect. And you got to get that intuition. It's not a natural intuition. I think maybe it's becoming a tiny bit more natural to people because there's a little bit more exposure to these things, but it's not something that people generically have. It's really worth getting because it's the foundation for what you can do. The other thing worth getting is sort of the methodology of very, very simple programs, kind of the idea of meta modeling, the idea of you've got maybe a model for some system that is itself an idealization of the system, but what is the meta model of that model? What is the truly foundational, down to the very essence, the very primitives version of that model? That's the thing that you can most effectively kind of investigate. And if you figure out something about that very essence of things, there is much more leverage about what happens in sort of downstream from that. Knowing the essence is going to tell you lots about what builds up from that. And I think I might say that in my own efforts, the fields have some moment where they get a certain methodology, they build up the field, there's certain foundational principles that are figured out. And then people say, well, we can figure things out from this. And they keep doing that for 50 or 100 years or more. And the field progresses incrementally. And the foundations of the field usually aren't talked about at that point. People just say, oh, that was figured out 50 years ago or whatever. There's nothing to do with that. What I've found is that actually often the foundations are poorly defended in a sense. You can go in and attack the foundations and make a lot of progress, particularly using new paradigms like the paradigm we now have that's this kind of multi-computational paradigm and so on that has to do with observers and multi-way systems and Ruliads and all that kind of thing. So there's a lot of progress to be made in I would say, almost any field. And where one is interested in kind of a global foundational understanding. This is get to the point where you can make that progress. It's both understand how to do rulology, do experiments on that, understand if you already know a bunch of mathematical methodology, understand how to plug that into what you can do with rulology and so on. And that's a sort of a big opportunity is kind of making bridges from these kinds of things that we're doing at the sort of foundational computational level, bridges to existing things that have been done in different areas of traditional science, whether that's biology, foundations of mathematics, physics, whatever else. And I keep on saying this, but I'm going to say it again. I think that, we know that our physics project plugs into many kinds of things that people have studied. It kind of gives both a foundation and an understanding of, spin networks, causal set theory, things about holography, things we don't know for sure about string theory, but we strongly suspect it. And one of the things that happens is if you can make that bridge, it's kind of a two-way story. Both you get to use the methods that we've developed for the physics project and so on to inform more about, let's say, string theory, and you get to use what's been figured out in string theory to inform more about our physics project. So it's very worthwhile to build that bridge. And for the sociology of science, it's also a very worthwhile thing to have happen because it allows one to sort of pull in a community of people to kind of be involved with what we can now make progress on that wouldn't otherwise have seen how they could get involved. So, it's learn to do computer experiments well, learn to use use Wolfram language. I will say that there are a few tips about what to do. I mean, again, when you make models of things, go simpler, 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 until you get so simple that it does nothing interesting. And then, but you'll turn out that you'll keep on saying it's not going to do anything interesting. It's too simple, and you'll be wrong. At least I'm still, after 45 years of doing this, I'm constantly wrong about that. And then don't worry so much about how you make the bridge to, this particular phenomenon. It's a very common thing in sort of reductionist science to try and reverse engineer nature, to try and say, we know there's this effect. What can that come from? What's the kind of reductionist way of doing that? Well, because you get to these simple rules, you get something that's roughly right, and then just run it and see what it does, and then try and make that bridge to what's actually observed. And the amazing thing is when that works, you have something very powerful, because it's not something where you tweak the model because you know this or that thing is true about the system. It's something where you got this model, and from so little emerges so much. That's the most powerful kind of modeling that you can do. So it's now, another tip about actually doing sort of computer experiments and studying these things, visualize early is an important tip. It's a very common thing to kind of say, oh, I'm going to do my research and I'm going to make my things I need to do research. It's all a bit messy, and I'll kind of make a beautiful picture at the end. Turns out, if you do that, you often get to the end and you make the beautiful picture and you say, oh my gosh, now I can see what was going on because I can actually see what's happening in that picture. Drat, I wish I'd done this much earlier because that my project would have gone in a different direction. So it's really worthwhile to to think through, how do you make the clearest visualization that kind of gets all the elements of the thing. I mean, our eyes are the best channel we have to get information into our brains. And, what, people will often sort of say, it's a tendency to say, I'm going to make it very scientific. I'm going to plot this curve. I'm going to get these numbers out. By the time you're plotting curves, you've probably lost the game. It's probably, if that's the main way you're studying your system, you're going to get, a favorite example of mine from long ago was people studying the growth rates of snowflakes. And they didn't realize that in their models, the snowflakes were spherical, which of course is nonsense. But they were just looking at the growth rate curves. So why would you ever notice that? But if you look down at what's really going on and you try and visualize that, you discover much more. So, another thing I would say is present your work as a computational essay. In a Wolfram notebook, you are using Wolfram language as a way to express what you're doing. I view Wolfram language as being kind of a notation for computation, in the same way a much simpler notation for mathematics that we have, the kind of plus signs and equal signs and so on. That's kind of a notation for math. What Wolfram language tries to be is a notation for computation. And it's a very expressive notation that has the great feature that if you write something down in that notation, it's completely unambiguous, and you can always run it anytime you want. And so, I see computational essays as being something which is kind of an expository presentation where some part of the meat of what's there is computational language, is Wolfram language. That's part of sort of explaining what you're talking about. And that's, I think, the direction to go in terms of sort of the output from things you might do. I think most people at this winter school aren't going to be doing large-scale projects, but that's the thing to do if you're doing even a small-scale rulological investigation, kind of building up a computational notebook, building up with computational language expressing what you're doing. That's kind of the methodological approach, I think, to use. Well, let's see. I don't know how long I yacked on here, but tried to give you a little bit of an introduction to things. I'm hoping, I think a lot of what we'll be talking about is things I've written, other people have written about this sort of real flowering a possibility in science right now with these kinds of methods. And I hope, I think an important objective for these couple of weeks is know the content of what we've already figured out. And then there's get the intuition, understand the methodology, learn the content that we've already figured out. And then go be ready to figure out more stuff for yourself. And there's lots of exciting things to do. And it's a great time. And I look forward to chatting more with all of you. It's always, for me, I really love to get to know all the folks who come to our various programs. It's sort of challenging in the amount of time we have, but I hope we'll have a chance to chat about different kinds of things. I guess we could, if people have, the general things that they might want to bring up, or questions. I think the more technical questions we should probably leave to other times and places. But if you have things you'd like to bring up, maybe I should say something else. Let's talk about Wolfram Institute a little bit. So, I do basic science as a hobby. That's what I've been doing for the last 40-something years. I kind of used to do it for a living, but I've been doing it for a hobby. I think I've been pretty productive in that effort, and had a bunch of people who worked with me, and they've done interesting things, sort of spinning off the things they've done with me. But a couple of years ago, we decided it's time to have a more organized approach to these sort of directions in basic science. We need to kind of create Wolfram Institute, which we've done, and I'm happy to say we've even got some funding for it from a variety of sources, not just me. And the Wolfram Institute is a place where we're trying to carry forward a lot of these basic science directions. I will say that the thing that I've done over the last 45 years or so in building technology companies and figuring out how to do very effective R&D is I've kind of got a shtick for sort of how to push forward R&D, how to do innovation in technology development that I think has been very successful. It's quite hard driving, and it's quite it tries to make the best use of everybody's talents. And I think we've been very successful at that over the course of many decades now in technology development. My goal with Wolfram Institute is to extend that methodology to basic science. And sort of a core of that is the things I'm trying to do, where I'm sort of figuring out the strategy. We're going to try and study economics or whatever else, and people are working with me. Hopefully, they will do things which, will let them write their own papers and so on that are probably more technical than the things I'm going to write, that are sort of parallel tracks of delivering the same fundamental scientific content. Then another big thing we're doing at the Institute is bridge projects, where we're taking things which we do have sort of our representation of that thing, but now we have to make a bridge to the way that things have been done in kind of academic research and so on in these areas. And sort of, it's like in biology, for example, we've got a lot of interest from biologists, but the paradigm that we're dealing with is very different from the paradigm they're used to. I mean, this was about a year ago. I was giving a talk to a group of theoretically oriented biologists, and I'm about 10 minutes in, and some enthusiastic person points at some picture of a cellular automaton and says, what kind of animal is that picture made in? And you kind of realize in that moment the sort of gap in way of thinking about things that we have between the kind of abstract thinking that we're doing and the kind of thing that's been traditional in biology. That's a very large-scale data-driven field at this point, where theory hasn't really been a big thing. So there's a lot of work to be done in kind of bridging the kinds of things that we've made progress on with the kinds of things that are sort of understood in the academic world of these different fields. Another thing we're trying to do at the Institute is tool building kind of open source Wolfram language tools that can actually do efficient hypergraph rewriting, or multi-way system things, or things for biology and so on, so that other people can be part of the story. I will say, by the way, one practical point: if you look at anything I've written, it has lots of pictures in it. You can click on any picture and you will get the code that makes that picture. And that is a super useful way to kind of start building on things that have already been done. You don't have to start from scratch, write your own code. You've got that code, it already has the nice visualization or whatever it is. Then you apply it to what you're thinking about. That's a very useful methodology. We're trying to build more tooling through the Institute to make more of that possible. And the fourth kind of branch of the Institute is outreach, and trying to take what we're doing and at a more human level kind of bridge it both in the world at large, creating expository writing. We'll have a science writer in residence program, for example, trying to get the things we're doing explained as well as possible. I try to do my part in writing things in an understandable way, but I'm writing at a particular level and to particular audiences, and there's much more to do along those lines. And also, we have a lot of people who are both sort of professional scientists and non-professionals who sort of want to interact with and understand what we're doing, and that's another function of the Institute. So we have opportunities at the Institute. including some paid opportunities to do things, and we'll be interested to chat with people about that. I think we've been trying to invent, as I say, I think I know a bit about how to manage technology development. We've been trying to invent a bit about how to manage scientific development. Now, okay, here's an even bigger challenge. One of the grants we got recently is about philosophy. It's about computational metaphysics. And so now the question is, how do you organize a philosophy project? It's like if you're building a product and it's a piece of software or it's a device, it's like you kind of know how that works. But philosophy is a field where people are still talking about the same things they were talking about 2,000 years ago. How do you organize a philosophy project? We're trying to figure that out. The prototype, what we're doing is we're trying to concentrate it by, we're going to create some books about sort of the connections between classical philosophy and things like the Ruliad and so on. We're trying to, and the goal is to create those artifacts, create those books. And so what we started off doing, I started off making a bunch of prompts about, how does the Ruliad relate to ideas of first causes and things? How does kind of our view of time relate to something that, Heidegger talked about? These kinds of things. They're kind of prompts for what is the relation between what we're doing in sort of classical philosophy. That's my attempt, at least, to begin to make that bridge. I think the next step there will be some sort of encounter groups between philosophers and folks who know about the science, then most likely sort of drafts of things from the philosophers, which then get commented on from a science point of view, and sort of try to iterate that towards a real kind of joint understanding of these things. I mean, it's a great opportunity for philosophy and some opportunity for the science as well, because the science really informs a lot of the long-time questions in philosophy. It kind of injects a new piece of fact, so to speak, into the philosophy. And from a science point of view, I think it can give us the possibility of sort of new ways to think about things. I mean, for example, one of the ones that's tantalizing for me is that I think there are properties of us as observers that we just completely take for granted, but which are things that lead to certain ways in which we perceive the world. So, for example, one of the big ones is, why does the world seem three-dimensional? We could parse the world by just thinking about it one-dimensionally, like a Turing machine. We could look at different elements of the world in that way, but we don't. We think about the world three-dimensionally. And why is that? Well, there's certain aspects of us. For example, one aspect of us is that we have mass. Depending on what we've been eating, it may be less or more, but or what our genetics is or whatever. But we're not massless elements. We're not massless entities. If we were massless entities like photons, we would have no notion of time. For the photons that were emitted at the last scattering surface when the cosmic microwave background was created, when that photon is absorbed by some detector today, no time has passed for that photon between the beginning of the universe and now. So the fact that we perceive time as passing is a consequence of the fact that we have mass. That's one example of something that is sort of an obvious feature of us that leads to a consequence for the way we perceive the world. Now, I think there are probably some others. So, for example, there are things that we believe intrinsically about the existence of objects. The existence of objects is not self-evident, that there can be a thing that maintains its identity through time, through space, and so on, is not self-evident, but is something very much burnt into our view of the world. That's another thing. I think that, another thing that's important is that there are lots of us. I don't think there will be a good notion of objective reality if there was just one of us. If there was only one entity that was kind of doing the perceiving in the universe, it's hard to have an objective notion, a kind of it's independent of me notion of what's out there in reality. So the fact that there are lots of us is important. And the fact that I think that we kind of are, in a sense, we are in a small piece of the Ruliad. We're very nearby in Ruliad. So our points of view about what's going on are very similar. It's like the fact that we're all on the same planet. And so when we look at the night sky, our point of view about the configuration of stars is very similar. If we were on a different planet, our point of view might be quite different. A different galaxy, our point of view about the configuration of stars will be quite different, even though we're in the same universe. Even though we're in the same Ruliad, our point of view about things will be different. Anyway, and I'm guessing that there are some almost philosophical points that will lead to, that will eventually say, aha, that's why we perceive the universe as roughly three-dimensional, and other kinds of things like that. So I think that's the trade from philosophy that we can hope to get. Anyway, I think that's we can talk a little bit about other methodological kinds of things. We've done lots of stuff with AI, and Wolfram language is a key kind of sort of grounding for sort of what LLMs can do and all those kinds of things. But there's a question of how do they get used in the kind of work we're doing with rulology and things like this. Basically, when there's something obvious, an LLM can tell you about it. If you've generated a sequence of numbers and it's something where there's kind of an obvious program, maybe it's a little bit too complicated for our existing find sequence function, the LLM can tell you. It's kind of a thing that it can tell you because it ingested kind of the literature of mathematics. It's kind of doing thematic searching of the literature of mathematics to say, where do I see a sequence like this? And I think that's a general thing that's very useful potentially, is thematic searching with LLMs. In fact, one of the places I'm hoping to use that is in trying to figure out kind of experimental consequences of our physics project. One of the cautionary tales for me is throughout the 19th century, all sorts of people like Boltzmann were agonizing about how can we prove that the universe is atomic? How can we prove that molecules exist? And they couldn't do it. They didn't do it. But actually, in 1827, a botanist named Robert Brown had discovered Brownian motion. Had Boltzmann really known about that, he probably could have said, yeah, this is, you can see there are molecules. Now, it mattered that there were microscopes that were good enough, blah, blah, blah. But that's that's kind of the key thing. But he didn't know that because he didn't have an LLM to do sort of a thematic search of the scientific literature to say, where do you see discrete jumps show up in what you might think of as a continuous motion? Actually, I should ask that question of an LLM again. But that's where one hopes that there's some effect, something in many-body quantum mechanics, some effect in astrophysics, where it's like, oh, there's this mysterious effect that we see in a gamma ray burst, there's some particular kind of thing. And then you realize, oh my gosh, that's a thing that relates to something that we find in our physics project. It's a lot easier to do that than to say, let's make a prediction. I mean, it's cool if you can make a prediction, it's validated, but that isn't the actual arc of most of the history of science. Usually, you make a prediction, it's hard to make the prediction. You don't really know whether you've got all the, electromagnetic propagation of this or that right for this gravitational lensing event, for the dimension fluctuation. If you didn't get it right, then somebody's searching for the wrong thing experimentally. Somebody does the experiment, they got to do a bunch of complicated data analysis. It's hard to know, did they get to the right answer? But if what you can do is essentially look back to an experiment that was already done, you have a much easier time of it. And that's what I'm sort of hoping is going to happen. And we'll see how it plays out.